Chemistry, good morning. Welcome to another week of e-learning. A couple things before we get started though. I'm going to send out a Zoom request for a meeting on Wednesday just to get, it won't be a teaching Zoom, it'll be a answer questions and kind of like talk to you guys about the rest of the year and how do we prepare for the exam type stuff. We're gathering more information about exactly how the test is going to happen. I know some of you have been getting emails from College Board, and that's good information. But just want to be able to help you in other ways. And how do you study? How do we get ready to be able to do this test well? That being said, we do have some more work to do here. Um, so I want to kind of jump right into this here. All right. We last assignment was doing some electron configuration, which for most of you is a review. Pretty straightforward, but what I want to go into now is how do we know that these electrons are in these energy levels and suborbitals? Okay, where did this all come from? And that comes from this thing called photoelectron spectroscopy. Okay, this is the crazy machinery that you'll see at universities that do this. And basically what it does is this, is we have a sample of a material that we are going to shoot x-rays at. And those x-rays are going to cause all of the electrons to be removed out of their energy levels. Okay, so we have our diagram here. We're going to shoot it with x-rays and they're going to get kicked off. Okay, and then we're going to have a machine that is going to record, okay, how many electrons that we have at different energy levels. Now, what does that mean, different energy levels? Well, think about the structure of the atom for a minute. We know that the closer an electron is to the nucleus, due to Coulomb's law, the more tightly it's going to be held, okay? Because distance affects attraction between a positive charge and a negative charge. Likewise, the outer electrons are not held as tightly because they are farther away, plus they are shielded by all of these inner electrons, which are going to repel or push against the outer ones. Okay, so as we go from the inner energy levels to the outer energy levels, we see a decrease in attraction. Okay, first because the distance goes up, but then also we see an increase in shielding of or repulsion between the inner electrons and the outer ones. Okay, so what does this mean for this chart thing that shows up here? Well, here's what happens is as we remove electrons, we're going to see more and more of them be removed at a higher energy level or more energy the closer they are. So this peak that I'm on right now, okay, notice that it's between the 1000 and 100 range on our energy chart, okay? By the way, on the bottom here, the energy is going to be in kilojoules or megajoules. It doesn't really matter what the version of joules is. It's going to tell us the same information. And basically, that these electrons are harder to remove than these electrons over here. Okay? So from that, I can tell that this is going to be the 1s, these will be the 2s, and these will be the 3s. Notice that there's a little bit of separation between the S and P's. Okay, it's because P's are actually a little bit farther away than the S's, but they're in the same relative area as each other. Okay, so they're groupings. Okay, they're on the same street. So how do I know that this is going to be the 1s peak? Well, remember what we said before, that the electrons that are closer are going to be more tightly held. The more tightly held an electron is, it's going to take more energy to remove it. These are harder to remove, and these are easier to remove. Okay, so we see them grouping up: hard, medium, easy to remove. Okay, so the 3s are going to be farther away, the 1s are going to be really close in. Okay, now as we add more protons, you'll actually see that all of these peaks will move to the left. Okay, that's because as you add protons and you become different elements, okay, those different elements pull in all of their energy levels closer and closer. All right, so how do I determine how many electrons were here? Okay, well, this first peak here represents the 2 electrons from 1s2. It's pretty easy to see that, okay? Um, so what we're going to do is we're going to base all of the other peaks and how many electrons in there based off of the 1s2. So if this is going to be 2 at this level, this is about 4, and this is 6. Okay, so 2, 4, 6. All right, so I've got 2, 2, 2, 4, 6, 2, and then here I've got 2, 4, and this one doesn't quite make it up to 6. This is going to be 5. So if I add these all up together, I will have 5 plus 2, which is 7, plus 6, plus 2, plus 2, that giving me a total of 17. All right, so if I have 17 electrons, what element am I? I am over here. I am chlorine. There's my chlorine. Okay, so this is a chlorine atom, and that's how you'd identify it. These are my inner electrons, okay, and these are my outer electrons, or my valence electrons. All right, I want you to take a look next at a couple of the assignments here. So first of all, I am going to put this in the quiz category. There's 2 assignments today. They shouldn't take you a ton of time, okay, but because we're kind of on extended lesson days here, I think you guys can handle it. Plus you don't have anything else to do. Haha, Netflix can wait. All right, so notice this sheet here, these look a little bit differently. Like, wait a minute, what happened? The other one were so nice, they're nice and linear. Here's how you determine what you're looking at. We're going to look at these values here, okay? Because these values are going to tell us where we're going to start as far as 1s2, 2s2. I have my little chart here handy. You might want to have that with you as well. I encourage you to print one of these off. It makes life a lot easier. Okay, but remember what we said. The more energy, that means it's going to be closer to the nucleus. Okay, so when I'm looking at this, I'm looking for my high energy. So 52.6, I don't know if it's kilojoules, megajoules. I don't know what it is. It doesn't actually matter. It just, I need to find the one that's the most. Okay, so this is going to be my 1s2 electrons. Okay, now I'm going to look for my second most. Now look how much this drops off. That drops off a lot. So these inner electrons really tightly held. Next energy levels, not so much so. So, and then this is 2s2 and then 2p4. Okay, so what element is this? Well, this element is going to be 2, 4 plus 4 is 8. All right, we've got our good old friend oxygen. So here's oxygen. All right, so over here, let's take a look at this. I'm going to write out the electron configuration real quick. 1s2, 2s2, 2p4. All right, and then our Bohr model. And I'm just going to do 2. All right, and I'm going to add these up together. Okay, so I've got 2 that are here, and I've got 6 that are here. Okay, and we're kind of doing the shorthand method. We're just showing where they're going to be. They'll actually spread out and look more like this if we're drawing it for real. And then we're going to put our protons in the middle. So P, and this is 10. Okay. Number of valence electrons in the outermost energy levels. Okay, that is 6. All right. All right. So there. That's how to do that one. Okay, I'll do one more. Why not? Okay, so once again, I'm looking for where's my 1s2. Those are my most tightly held. Okay, Coulombic attraction says if I've got a short distance, I've got no shielding of other electrons. Okay, then I have my my 1s2. Now this is a 0.42. Those are going to be my outer ones. 347. That's my 1s2. So 1s2, 2s2. 2p6. I'm just going backwards. Okay, the p is going to be less tightly held than the s's. And then 3s2, 3p6, and 4s1. Okay, so we'll rewrite this here real quick. 1s2, 2p6, 2s2, 3p. Oops, sorry, 3s2, 3p6, and 4s1. I like to put the lines on these so I can see where my energy levels are. I've got 1, 2, 3, 4 energy levels. And why not just take this and put this down here? This is my valence electron. Now, I want to show you something with this. This is a nice little thing. 4s1, who has 1 valence electron in the 4th energy level or 4th period? 1, 2, 3, 4. This is potassium. Okay, that's potassium right on there, and I can do that, okay, because the periodic table follows this filling order. These are the last. This is where the last electrons goes in all these energy levels, and there's 4s1 right there. So there's a couple ways to getting to what it is. You don't necessarily have to add it all up. So this is potassium, or K. All right. So here's my drawing. 1, 2, 3, 4. I've got 2, and then 8, and then 8, and then 1. Okay, so there we go. We have our Bohr model drawing. Okay, and this guy is going to probably lose that electron. Potassium likes to do that, and we've got our 19 protons in the middle. Okay, so I'm just going to let you finish that up. That's how those work. Grab the other worksheet that we have. Okay, so take a minute. I'm going to pull it out. I'm going to go through a couple of things in here. Most of this is review, but just want to point out some helpful tips to help you out here. All right. Let's see here. Bromine, where are you? 35. Okay, so the first one here is just some electron configuration work. Okay, so I'm going to show you the short version of how to do this. So bromine is sitting right here. It has element number 35. Okay, so 35. And I'm going to start off by doing the full electron configuration. And the full configuration is this: 1s2, 2s2, 2p6, 3s2. That's 4s2, 3d10. All right, so there's our complete diagram. So how do we do the noble gas configuration? Okay, well, here's bromine, and what we're going to do is we're going to use argon to take the place of the first 18 electrons. Okay, so here's the noble gas configuration. We'll put argon here, okay, and that is going to take up the first 18 electrons. And then I'm going to count on here. So 2, 4, 10, 12, 18. I do not have to rewrite this because the argon takes the place of the first 18. I'm just going to take the remaining electron configuration, 4s2, 3d10, and 4p5 to fill in the last. Okay? So that's how we do the shorthand version. Instead of writing all of this out as well, if I find... So I go to bromine, I find the noble gas that is just above and to the right of it, and I use this to take the place of the first 18. Now let's say I iodine. I do the same thing, is I would take iodine, I would go up and to the right, I'd find krypton. Krypton would become my base. I would put krypton here, all right, and then I would continue from there, okay? Krypton, its last electron configuration is 4p6. Okay, so what that means is this is when I'm looking at my chart, 4p6, I would start next with 5s2. So that's one way to do that. Okay, that should B review. Um, let's take a look at this. Okay, in which block are these elements found? All right. Well, that's related to this chart here and where last electrons are. So let's find SC. SC is this element right here, and notice that its last electron is a D. Okay, so this is considered the D block because these are the last electrons that will fill. So this is my S block, this is my D block, here's my P block, and here is my F block. Okay, the block is just where the last electron goes. All right, so there's two. There's one other thing that I wanted to show you. Let's see here, maybe two. All right, let's do this. This is number 6. This comes up sometimes. All right. So, given the electron configuration of the following transition metals, so we have Sc plus 3, okay, and Sc is right here, okay, and it has 21 electrons. So 21 electrons. Now, plus 3 means that this has lost 3. So 21 minus 3 gives me a new total of electrons as 18. All right, so I'm going to go up to 18. So 1s2, 2s2, 2p6, 3s2, 3p6. Let's see, what am I at? 2, 4, 10, 12, 18. Okay, so this equals Sc plus 3. Now, I also want to show you this because if this is 18 electrons, this is also the electron configuration for argon. So when we have ions, a lot of times we will have things that will match other elements in their non-ion format. We actually call this being isoelectric. Okay, and that shouldn't really surprise us because Sc is here with 3 valence electrons. They're weakly held. If it loses those 3, it's going to revert back to the electron configuration of a noble gas. Okay, when we are losing electrons becoming ions, we're either gaining electrons to become like in a noble gas, or we're losing them to become like a noble gas. So that's how you work the problems in 6. The last one I wanted to look at is this here. Okay, now I showed you this earlier, and this shows that the electrons are paired together. Okay, so even though electrons are negative and they repel each other, they do this weird thing where they pair together as buddies. Okay, and so I want to show you how to use this chart to show where the electrons go in their suborbitals. So, for example, vanadium has 23 electrons. Okay, so 23, and we're going to show these electrons filling their suborbitals as a pair. A set of up arrows and down arrows. So this equals 2 electrons. This is electron 1 and electron 2. And they do this thing where they spin, okay, in opposite directions. You can kind of think of it as if they are going to a camp. And in their room that they're sharing, these 2 electrons are sharing, one's going to be on the top bunk, one's going to be on the bottom bunk. Okay, so this is still going to fill the same way as we did here, okay, but in the individual suborbitals, okay, it's going to be a little different, okay. So what's a suborbital? Okay, so this is an orbital, this is an orbital, here's a suborbital for the p's. So s's have 1 suborbital, p's have 1, 2, 3, d's have 1, 2, 3, 4, 5. Right, and F's have 7, but we don't do this for a lot of things that have 7. We don't really get into those elements. Okay, so what do we do with these 23 electrons? Well, we are going to first fill 1s2. Okay, and it gets 2 electrons. So there's 2. And then we're going to fill 2s2. It also gets 2 electrons. Right? Now, for when we get into boxes with when the next energy level, we're going to first fill each one of these rooms with 1 electron. And then we're going to go back and fill it with the second one. And it doesn't really make sense quite yet why we do that. So I've got 2, 2, 1, 2, 3, 4, 5, 6. Okay. And so that puts us at 10 total. And I'm going to put 1 up, 1 down. Now I'm going to go up, up, up. Okay, because these are technically separated. So I'm going to fill 1 suborbital first and then move on to the P's. So this gives me, let's see, how many do I have left here? I've got 23 minus 10. I have 13 left. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to fill both of these as well. These are both going to double fill. So this is 2 and 6. So at this point, I'm up to 18. So I have 5 electrons left, and those 5 electrons are going to go in the D suborbitals. Now, each suborbital can hold 2, but we start by filling each one with 1. Okay? And then we would go back and fill with a second. Okay? So this one here actually has 5 partially filled D suborbitals. They only have 1. All right? If I had another one, if I had 6 electrons, then we would do the double filling. Okay? So this kind of goes back to that camp analogy with bunk beds. You're only going to want to fill 1 bunk at a time, or 1 bed at a time. You're not going to put 2 kids or 2 electrons in a top bunk and a bottom bunk. You're just going to put 1 in there until all the beds, all the double bunk beds have 1 kid in them. Then we'll put a second kid in there. Okay. In this case, the kid is an electron. We'll put a double one in there. Okay. So this is the electron notation that comes with that. So these d suborbitals are going to partially fill with 1 electron before they double up. Okay. And that's just kind of how this works. All right. So let's answer this question down here. Number of unpaired electrons. Okay. Well, these 5 here are not paired. There you go. There you go. Okay. So that's the basics of that. All right. So there's a bunch of work today on this, guys. Hopefully a bunch of it is review. And hopefully you guys are doing well. If you have any questions, please let me know. Anything we can do to help, we will. All right. Have a good one.